allow the voltage, and at higher frequency it will start allowing the voltage till f equal to infinity. And then we take the output across resistance. So as we spoke earlier that we had same structure, but we took output from this side and gave input to this structure, and now we are taking output from this thing, so that makes it a high pass filter now. So in this circuit arrangement, the reactance of the capacitor is very high at low frequency. Xc is higher at low frequency, turning out that it will not allow the input signal through this capacitance, because let's say if we are having a DC signal, so capacitor is open for DC, so it will not allow. After the cutoff frequency is reached, after this Fc is reached, what will happen? The circuit will allow some of the voltage to pass through it, and after increasing the frequency more, we will have all the voltage available across this thing, because this resistance would be higher as compared to the drop associated with it. Okay, so this is the high pass filter. First order high pass filter is having same frequency equation as the low pass filter, but only the difference is that its structure is different. Its structure is that we take the output from the resistance instead of capacitor. The Fc is 1 over 2 pi Rc, and the phase is tangent inverse R y divided by x of this total z. Okay, but this is the phase, so this is calculated from the omega's equation. Okay, so now if we want to calculate the output of this circuit, so V out would be V in and multiply by same voltage divider rule, but here we are having R divided by R plus Xc now. So square under the root will give us R by Z. So R by Z is giving us the voltage gain. The voltage gain will always be lesser than 1 because we are having R plus X greater than R always. So this is the typical high pass filter. If we examine the curve of this response, so we will have a 20 dB per decade increase till we reach this 3 dB 45 degree minus 3 dB 45 degree point, and after that we will be having our pass band. So pass band is for higher frequency. At low frequency the capacitor is working, and at higher frequency the capacitor is short, it is not working. So if we graph its equation, it will be something like this: Xc divided by this thing. In previous equation we had Xc above, so due to that we had minus 90 degree, as Xc is 1 over j omega c. Now the Xc is in the downside, so 1 over j omega c will make this thing j to go up. Are you getting my point? In the first equation we had Xc divided by R plus Xc. So we had this 1 over j omega c that was making a minus 90 degree angle. Now we are having R divided by R plus 1 over j omega c. If we make this thing go up, let's say this R is not here, what will happen? This will be j omega c. So j is 90 degree plus. So this will start from 90 degree, and at higher frequency this will become 0. So this is the only difference, that we had the phase of 0 to minus 90 in the previous, and plus 90 to 0 in this one. So again, C always causes a 90 degree phase shift, but depending upon the voltage divider circuitry, that where are we taking the voltage, it can be from minus 90 to 0, from 0 to minus 90 or from 90 to 0. So this is what happens for capacitors and inductors. Let's study an example on this FC. Calculate the cutoff breakpoint frequency. So cutoff frequency is also known as breakpoint frequency. Remember this thing. Okay. For a simple passive high pass filter. Passive means that there will be no positive gain. High pass means that we will take output from the resistance and it will be like this. Okay, considering that an 82 picofarad capacitance is introduced in the series with a 240k ohm. So this is 240k, this is this thing. So FC would be equal to 1 over 2 pi RC. So put these values in it and we will get what? 8k hertz. So if we draw this thing and this is our 8k, so what will happen? This will be something like this. So at 8k we will get our 45k point or minus 3 dB point, and after that we will get our required desired signal to go up. Second order high pass filter is same as the first order, but we are using the repeated stages. So first stage, first filter, and second stage again first filter, but with some different values, say C2 and R2. The FC, the cutoff frequency, the corner frequency, or the which frequency, the breakpoint frequency, is 1 over 2 pi under root R1 C1 R2 C2. Why we are taking under root? Because if you multiply R with R and C with C, they go R square and C square, so we must have an under root with it. So now it is R1 C1 R1 C1 and R2 C2. So this is what happened. That's why this under root came into being. Okay, so this is the high pass filter. Let's discuss the use of this high pass filter. High pass filter allows high frequencies. So if we have a square wave like this and we give it to a high pass filter, it will only allow this first peak and then allow its second peak. So for first peak it will go up and then end up, and for the down peak it will go down and then this. So this is something like the shimmer's trigger. Shimmer trigger triggers a circuit with a pulse. So if we, let's say, use some diode with it, it will become like this, just like that pulse which we give to the heart patients if we want to stabilize their heartbeat, or if we use same we can also use it in the same MRI instruments or the graphing instrument, the ECG instruments, cardiographic instruments. So this structure with a little modification, a high pass filter, a capacitor, and the voltage taken from resistance is taken with a pulse given for such thing. So this pulse has benefits. This gives high energy at a very lower time. So high energy at lower times gives us what? A jerk in some scenario. So if you want to increase this jerk, now if we want to increase this, we want to give more energy. What will we use? We will take the output from this point. So at this point this will be something like this. So some of the frequencies are removed, some are not removed. So this is it for the high pass filter, that we can use it for cutting this second edge or reducing this second edge. Now band pass filter, as the name suggests, it is allowing a band of frequency. Say 2 points, one will be start allowing the band. There are 2 points, one will start allowing the band and other will delete the band. Band pass filter can be used to isolate or filter certain frequencies that lies within a particular band or range of frequency. So we are having two let's say bands here. This one is rejected, this one is rejected, and this one is pass band. So a band pass must be of this sequence. First, it should be having a high pass filter. Why? Because we want this thing to be passed. So if we have a high pass filter and we have, let's say, this band, what will happen? This, let's say, this thing would be passed by this filter. After that, we will introduce a low pass filter with it. So what will the low pass filter do? The low pass filter will delete the higher band that is not required. So let's say this is a low pass filter and this band is deleted, this is not required, only we are remained with this band now. So first we had removed this one. Let me mark it with some different color. So first we removed this one and allowed this whole high pass, and then we removed this one. So this should be the sequence, that first you should have a high pass filter and then you should have a low pass. So this is a high pass. At high frequency it will start allowing voltages, and this will start working at low frequencies. So once the high pass is done, then this low pass comes into action and removes this band. So this band, this band. So this band was removed first and this band was removed second. This is removed because it is a high pass filter. So high pass and then low pass, and this is our required band. So this is what happened in this circuit. It can have such broader range, or it can have a short range of passing. In such cases it will be a very high tuned filter and can be narrow or wide band. So this is a wide band filter, this is a narrow band filter. Frequency response of band pass filter is discussed earlier, that it allows certain frequencies starting from lower frequency and ranging from a higher frequency in a pass band. So we are using two circuits, the high pass filter and low pass filter. So this is FL, and this FL was actually taken by the high pass filters FC. This is FH, the higher frequency. This is low pass filters FC. So we have two passing and cutting of frequencies, and both will be 20 dB because they are not occurring on the same point, they are occurring at different point. High pass filter starts from 90 degree and comes to 0, and low pass filter starts from 0 and goes to minus 90. So the phase is from plus 90 to minus 90, whereas the magnitude is from FL to FH. FL minus FH, FH minus FL, or FL minus FH is termed as the bandwidth of the filter. So high bandwidth would require this FH to be higher and FL to be lower, and we can decide about this bandwidth from the RC circuit that we are combining. So if you know low pass and high pass, then band pass is designed by combining a high pass filter with a low pass filter, and this is V in and this is V out. High pass is first, low pass is second. This is an important thing, please remember this thing. Okay, let's solve an example on this. A second order band pass filter is to be constructed using RC component that will only allow a range of frequencies to pass through 1K hertz frequencies. So this is the 1K hertz frequencies and below 30K hertz frequency. So this is actually system that is allowing some, let's say, audible range from 1k to 30k is around 20k, and that 20k is an elevated audible range if you just elevate it for some encryption or for better performance. Okay, assuming that both the resistances are 10k, calculate the value of capacitances. So this is a reverse problem. We have frequencies and we want to calculate capacitances. So Fc is equal to 1 over 2 pi Rc, and this C needs to be calculated. So R is constant. First put Fc here and make this thing here 1 over 2 pi F and R. So put this thing as 1k and then put this thing as 30k to get our C1 and C2. So after this we got this 15.9 nanofarad capacitance as C1. This was the high pass stage 1 capacitance. Now for stage 2 we calculate the low pass capacitance. So low pass capacitance is calculated by the same formula, and this formula states that C is equal to 1 over 2 pi Fh and R. R is same, Fh is 30k now. So 30k will be introduced here, and this turns out to be 530. So the whole design of the capacitor is that we are having 10k here, 10k here, and a high pass filter is here, so 15 is here, low pass filter is here, so 560p is here. So this is the circuit that we intended to design. Central frequency of second order band pass filter is very much important, because at this is the frequency at which the circuit is tuned. You can pass a signal on this point with a very better performance, so this will not be attenuated. So central frequency is actually the geometric mean. Geometric mean between two number is calculated as this: m is equal to n1 and 2 under the root. So geometric mean is FL into FH under the root. So geometric mean of that previous filter would be 5.48 kilohertz. This is point, not comma. So this is the circuit and this is the geometric mean for that. Low frequency is minus 30 dB cutoff point and high frequency is plus 30 dB cutoff point, so do remember this. We sometimes introduce stage buffering before going to the low pass filter. So we first do the high pass filter. We first introduce high pass filter and then we amplify this thing. We make this thing bigger, and after that we pass it through a low pass filter. So this is a bit more we say getting more gain due to this isolation buffer, and this is used because sometimes the effect of this circuit might cause some disturbance in this, so we have separated these two circuits by introducing this gain buffer. So far we have studied low pass, high pass and band pass filter. The next topic is the band stop filter. So band stop filter is sort of inverse band pass filter, and its central frequency is same as that of the band pass filter. It is a geometric mean of FL and FH, so no doubt that these two filters will have FH and FL calculated in the same manner. Okay, the band stop filter is formed by combining low pass and high pass in parallel. In that case we had cascaded it, so this was a high pass, this was a low pass, and this was our band pass filter. So band stop filter would be a high pass, a low pass, and then combine it for the signal input. So this is stated in here. The name indicates that it will stop a particular frequency. Since it eliminates frequency, so it will be also known as the elimination filter or rejection filter or notch filter. As we previously discussed, that notch is something like this thing. Notch is the cut in the fabrics that the people do when they stretch the clothes. Okay, in practical, due to the capacitance switching mechanism in high pass and low pass, the output characteristic might not be same as these steep lines, but rather would be something like this. So it will not be ideal filter. The electrical design is either that way, or we can also write it like this. We can draw it like this, that we are having resistance in series with inductance and capacitance. And what will this inductance do? At low frequency, this inductance would have XL equal to 0, but this capacitance will make this thing open, so the signal will appear here. At some intermediate frequency, this capacitor will become short as well, so this will ground the signal for that intermediate frequency. And at higher frequency, this will become short, but this will become open, so again the voltage will go through this. So the voltage was going, and then it was grounded in intermediate, and then like this. So this makes this thing the band rejection filter. Its system response, or V out, can be calculated as V in multiplied by the resistance, the impedance in this and this, so we will call it ZT dash, divided by R plus ZT dash. That will be equal to our V out. So ZT dash is XL minus XC, so XL minus 1 over omega L minus 1 over omega C, divided by R plus this thing. So this gives us the formula for the output voltage at any frequency. You just put the frequency in it, and it will give you the output in terms of that frequency. So this was a bit about the electrical design of the band rejection filter. I hope you people have gotten some idea about the filter design and its mechanism of working. If you people want to learn more about it, I have put some links in it. It has a low pass, high pass, band pass and band stop filters with passive filters background. So there is no active filter on these links. You just go to these links and you can find the classwork, etc., the timetables, or the weekly distribution, the CLO distribution, PLO distribution on our official site. Also, I would want to write the link of, but let's not write that. We are having a slide share account. You can go to this site, and from here it will guide you to the our slide share account. So you can also go to your slide share account and search for these lectures as well. This lecture will be having the same topic, passive electrical filters. So you can go to it and just check it. Okay, this is it for today. Thanks for watching this whole tutorial and video. Thanks a lot.